Okay, we can, let's start. It's 11 o'clock. We have certificates here. So if you need the certificates, feel free. Yeah. I'm going to forget, so if you don't want to get them, feel free to come and pick them up now if you need them. Before I also forget, this afternoon at 1:30, Rudy Abzol will be starting the next module with a keynote lecture at 1:30. I don't know if it's this room or that other room. If you're interested, you are welcome to join for the lecture at 1:30. And then also, before I forget, and if I forget to remind you afterwards, please let me know. There is a feedback form that we would like you to fill in. I think it's only kind of 8 questions. It shouldn't take more than 5 minutes to do. So if you could please fill out the feedback form. That is, there is a link on the Institute Piazza page, feedback survey. So it's anonymous. This link will get you, I think, to a Google form. So if you could do that before you leave the room, that would be great. Thank you. Right. So we are now ready for the last session about interactive visualization. So we are going to, maybe not explicitly, but see some of the concepts that were discussed that Niels mentioned, but also that Michelle mentioned in her first the opening keynote. For example, linking data in different visualization, different types of representation. So we select something in one case and then it highlights, or one plot, the same data point is highlighted in the other one. I'll show you some example of proteomics visualizations where linking is implemented. When we think about interactive visualization, this generally happens in the browser using JavaScript in the backend, but we will write our code that will generate JavaScript code, and this visualization happens in the browser. And sharing of these interactive visualizations is also an important concept, and I'll also kind of mention it and show you some examples, some motivating examples. And so there are two parts to this session. The first one is producing kind of interactive graphs on the fly, a little bit like we did for our static visualization. And then the second part, we will develop slightly more kind of long-term or long-lasting applications, interactive applications to visualize the data. So that the second part will be using kind of the Shiny package. But before that, I'd like to briefly demonstrate a package called GGBase. And to kind of actually demonstrate GGBase and the other packages later, I'd like to use the CRC dataset. So I'd like to read this dataset, and I still have it in my data directory. CRC train as a CSV file, and I'll call it CRCDF, like I've been doing since the very beginning. So the CRCDF data frame here, CRCDF, contains 200 rows and 79 columns. 72 of these, the 72 first are proteins, and the rest is metadata. So as you have already learned, or you already know the syntax of ggplot2, the syntax of GGBase will look pretty familiar. There are slight differences, but it will generally be look familiar. And instead of using a kind of ggplot function to create our plotting option, with GGBase we use the GGBase function. And the first argument is the data set that we want to use, like ggplot. And then we need to kind of map our axes, xy, like we did with ggplot2, except that in ggplot2 this is kind of comes inside the statics AES function. Here we provide this directly to the GGBase function, and it has a slightly different syntax. We need to use the tilde. So for example, here I'm going to take the two first proteins in my data set and tilde, oops. And the second one was AFM. And I'm going to store this in an object P. This object knows about the data and knows what columns to map to the X and Y axis. And then I'm going to build the visualization, a little bit like we did with ggplot2, but in this case we use the pipe argument and not the plots like ggplot2. And here we kind of build our plots by adding layers and not geom objects. For example, here the layer points. So if I execute this, the visualization pops up here in RStudio. Couple of additional customization that I can do. Along the lines of what we did with ggplot2, when I do my mapping, my axis mapping, I can also here map the filling of my points, for example, using the group metadata. And as before, if I now, wrong keys, P, and then pipe this to a layer points, I will generate these figures here. That could always be kind of exported or downloaded to SVG. So in addition to the fill here, other arguments that we can use are, type this here, would be to specify the shape, and then layer points, to use to differentiate the two groups using shape, and so on and so forth. So there is much more to GGBase that we will see, and in the lecture material I have links to the documentation and tutorials. But what we are interested in this session here is to add a little bit of interactivity. So I still have my plot here. So as you can see, if I just call the variable P here, it guesses what kind of layer, what kind of representation I need to do. And here it does guesses layer points. So if I want to add some interactivity, I can do that by setting, for example, or by controlling the size of the points using an input slider. So I want my input slider to start at 10 and finish, for example, at 200. And then maybe I will want also to control the alpha channel opacity using another input slider. That would start at 0 to 1. 0 being completely transparent and 1 completely opaque. And the syntax here with the tilde refers to variables in the data. The syntax here, colon equals, represents kind of constants and not the variables in the data. So if I execute this, I have the visualization here, my same plot, my scatter plot with intensities of my two proteins within these 200 samples, labeled with different colors, and I can here control the size of the points and control the opacity of the filling. So as an exercise, maybe later, I'll move on to the second interactive visualization package, Plotly, but if you want to do an exercise here, what you could do is to take one of the data sets that we used, for example, the Mulvey data set, run a principal component analysis on it, and then visualize your PCA interactively using input sliders, for example, to change the size and the opacity. But I would like to move on to another package that I don't know very well, but I think has really great potential, and that's Plotly. And by the way, if you don't have any of these packages installed, you can install them from CRAN. I did this a couple of minutes ago on this computer. And so so there are two ways to build Plotly visualizations. One would be to create these Plotly plots representation of data. But the other one that comes very handy, given what we have done before, is to start by creating ggplot2 visualization. So let me reproduce one of the ggplot2 visualizations that we did yesterday, using the CDC data frame, mapping my aesthetics. I'll take the same genes as I had before. Y equals AFM, and I will again use a color, but this time, for example, gender. And I will add to this kind of geometric object, visual representation using points. And let me store this into a variable P. So at this stage, P can be used, can be printed to. Oh, I probably need to stop this. Yeah. And sorry, if you didn't see what I had to do here, let me rerun this this line. So in ggplot2, it's displayed here in the viewer pane, but to stop this interactive visualization, I need to press the stop button or Control-C in your console, and this allows for R for the console here to start again, to take control. So I have my ggplot representation, CDC, not found. CDC, oh, yeah, CDC. CRC, yes. Thank you. So my ggplot2 object, as we have produced before. And now, what is very nice, very powerful, is that we can now pass this object, this ggplot object, to the ggplotly function from the Plotly package. and it will be automatically converted into a plotly visualization. Using RStudio, it's again displayed here in the viewer pane. If you're not using RStudio, it would start a new browser. That is essentially a new browser. Okay. So here it is. It now looks a little bit weird because the size of my screen is small. So I can hover, I can zoom. All these features here come for free by default with Plotly. Oh, okay. All right, interesting. File, open, file, open project. Here it is. Has it saved my file? Not the last one, doesn't matter. Oh no, it has not. Ah, no, here it is. So let me library tidyverse library. I will also need grid R. I read my data in. I load here. I produce my ggplot. And let's try again, and let's hope it doesn't crash because there are a couple of other figures I wanted to show. Yes, I like to live dangerously with my live coding. So here we go. So here's one example with hovering, producing, kind of giving the coordinates and the annotation of the individual data points, and I can here zoom in. I can zoom in. Okay. Okay. Inside my plot, and it works relatively smoothly. And it crashes RStudio. So apparently you can zoom in, you cannot zoom out. Well, at least on this computer with RStudio, it did work with my computer. Okay, and I did not save. No, my file was saved. All right. Well, this is a bit embarrassing. I will maybe reduce the number of ggplotly figures that I wanted to show. Actually, no, what I'm going to do is I'm going to switch to the lecture notes, and I'm going to show the visualizations on the lecture notes. This one. And something that is quite nice. So the lecture notes are produced in R Markup, that is automatically compiled into HTML, and it's very straightforward to embed these plotly figures in an R Markup. I didn't do anything special. I did exactly the same thing as I showed in the R script in my R Markup. So here I produce using the CRCDF dataset, but I subset 10 samples, 10 first and 10 last samples, and 3 proteins and 1 annotation, which is, or 2 pieces of annotation, sample and group. And then I transform this data from the wide to the long format with gather, as we have done multiple times throughout the course. And then I produce a ggplot2 here with my sample along yet, my intensity here that I call x on my y-axis, and I want to group and color my proteins and visualize this on lines using a geom line, and I visualize it here using plotly. So these line plots here represent the intensity of my 3 proteins here along my samples, first set of 10 samples, and second set of 10 samples. And for each point, I can verify one sample it is. It's a little bit difficult to visualize here along the x-axis, my value for x, for my intensity here, and which protein, VTN, which is intensity. And so I played a little bit with plotly, and I thought, oh, that's actually quite nice. Well, let's try to generate these data, or generate plotly representation with some mass spec data. So yesterday, at the end of the day, we looked at the MSN-based package to kind of read raw data in. And iTrack data is a kind of a small dummy data set with iTrack quantitation. So here I extract the first spectrum. All the spectra here in this test data set are MS2 spectra. And I say plot iTrack data, my first spectrum. So this is in kind of a full experiment object, double square bracket operator to extract one single spectrum. And this is my ggplot implementation to visualize a spectrum in MSN-base. And here it is. And now if I pass this MS2 variable to ggplotly, here's what we get. A ggplotly figure where I can now look at my individual peaks. But I think the zooming feature is quite nice. So for example, if I zoom in here on this region, so unfortunately, apparently the kind of axes are not updated automatically. But here I have my 4 report ions for my TMT, 114, 115, 116. So these are the peaks that are used for quantitation. Oops. Let me zoom back out. I'm not expecting this to crash. Does he say confidently? Yes? No? Good? Right. So I thought that was actually a pretty neat feature that allowed us to kind of zoom in, and despite the fact that, of course, unfortunately the MOZ scale is not updated, but we see quite nice resolution here of our peaks. That comes essentially for free by taking this ggplot2 visualization of overall data. And so here's another example. This is my TMT11 MS3 data set. My first spectrum here is an MS1 spectrum. That is represented here. This is the static visualization. But then I pass this ggplot object to ggplotly. And so here it is. And I can now zoom in and visualize the kind of isotopic envelopes of that ion. 669.9, 669, 67. Okay, so this is not not a good example, maybe. Which one did I take earlier? 5753, 5776. Okay. Yes. Why why do these go up? It should go down. Oh, no, sorry, that's correct. So 5668, 5673, so these are doubly charged ion, and here we have the isotopic envelope of that ion. So I was quite pleased to see how kind of seamless this is to apply it to our mass spectrometry data that we have seen yesterday. Okay, so Plotly and GGBase I think are very nice when we want to create interactive visualizations in the same way we want to produce our static visualization, to have a quick look at the data, but not necessarily to produce something that is kind of long-lasting or that we want to share with others. Although Plotly, it is possible to share Plotly figures with others. The way I think it's kind of most appropriate is to use it interactively. If you want to create more long-lasting applications with interactive visualization, then probably Shiny is a better fit. And so to start Shiny, I wanted to show you two kind of motivating examples how Shiny has been used to produce applications for proteomics. Okay. And Sarah is going to show us her first application for the kind of longitudinal QC. Oh, do you need to switch it?
No.
Ah, okay.
So this one is.
That one is connected.
So this MS-Stats QC is one example of the Shiny infrastructure in R that provide an application for mass spectrometry proteomics. And the term QC here is for quality control. So this application focuses on quality control, and especially for experiments that have a long running time and have many replicates. So what is important in these experiments is that to make sure that the measurement system, which is the instrument and also the sample process, work perfectly. And to somehow determine that, we have to distinguish between biological variation and instrumental change. In order to avoid biological changes, what we do is that we use the same samples that have the same protein abundance. When we do that, we make sure that, okay, we don't have any biological variation. So if we see any changes in our experiments, that is due to instrument change. And it is good to figure that out early in the experiment. And what this application does is to help us to diagnose these instrumental changes early in time. I would like to show you a little bit a demo of the application. So it is in the MSStats.org website, and there is a tab called QC, which has this MSStats QC application. So here you can see the VNet for that, the cheat sheet, and also the paper that we worked on here for more information. And here is the link for the MSStats QC Shiny app. As you can see, we provided several tabs. For example, this one is for importing the data. So you can import the data of your choice or just use the example data that we provided, and I will use the example data here. So if we upload that, you can see the data here, and here are your metrics, the 4 metrics that this data has, and your data can have more metrics as well. And then we with this Shiny app, we have the ability to just go over many situations and change things based on our needs. So for example, I will go to options here and I will select the metrics that I want to do further analysis on. So I will select all of them. And also we can choose the peptides that we want to do analysis on. So here you can see the list of all the peptides in your own data. So if you change your data set, then this list will also change it. So I will select all peptides. And then we have some decision rules here, which I will tell in a minute to you guys. So the quality control charts that we work on are these 3 quality control charts: the XMR, QSUM, and change point analysis. So in the experiments that we have like many peptides. So as you can see, we have a list of all our peptides here and the plots of retention time for each of the peptides. And you can see that the plots are all written in Plotly, as Laurent just described, so they are interactive. So by hovering onto them, you can see the actual X and Y value of each plot. And you can see that for this specific peptide, for this run, these 3 runs, the peptides were out of control. But for the rest, everything was okay. For this peptide, for example, in most of the runs, everything was out of control. And you can see that for all the different metrics and all the different peptides. So it is hard to decide, okay, if everything is wrong or not. So this specific peptide may have some problems for some of the runs, but if you change that to other metric, then things might be different. So everything is all right, and only in one run we have a problem. So since it was hard to look at different kind of metrics for each peptide to decide if things are wrong or not, we added a decision rule criteria here in which you can decide when we will call a process is a system performance is acceptable or not acceptable. So for example, we will say that, all right, if the percentage of out of control peptides are 70% or more, and then if 2 peptides out of the 4, if 2 metrics out of the 4 metrics that we have are out of control, then we will say that the system performance is unacceptable. And you can set some other criteria for when the system performance is poor. So if we set that to like 50 and then 1, and then look at the decision map here, it will show that, all right, for most of the cases for this specific metric, the performance of the system was okay, and it passed all the quality control exams, for example. And then you can play with the decision boundary rules and get basically different results. So this the plot has changed from the previous one. And this is the beauty of using a Shiny app, in which it makes you to do your experiments easier and faster. I think that's it.
Thank you very much. And I would like to show you a second example that was a data set that we have already seen, and a kind of some of the functions that we have already seen. So if I load my Prologue data package, and here I will use the Hyperlopid data set that we have used already a couple of times. And among the ways that we have used it was using a function from Prologue, which was called plot2d, to represent this 20-dimensional data along 2 dimensions, using by default a PCA, but we have seen other representation as it is here. So this is the kind of static representation of this data. But we very quickly realized that although it is useful, and I spent a little bit of time yesterday talking about this plot in particular and what kind of conclusions we can take, we realized that it would also be useful to have an interactive way to explore these plots. And so for that we created a package called Prologue GUI. So you see a pattern here. We have Prologue data, and now Prologue GUI. And they all come from Bioconductor. So I used BioC Lite to install Prologue GUI that wasn't available. So using Prologue GUI, I can use now instead of plot2d, the Prologue Viz application, to run this locally to visualize my data interactively. So here is the PCA plot that we had before, with the annotation, so I can add or remove annotations here interactively. I can play with the transparency. I can zoom in certain regions. And what I can also do is to select individual proteins of interest by clicking on the PCA plot, or also here below there is a table that lists all the proteins that we have. So I can also click on a protein in the table, and they, as you can see here, it gets labeled on the PCA plot. So when I click on this one, it also got selected in the table. When I click in one of the table, it also gets selected there. You can also search the tables here, and I think that's something I demonstrated yesterday towards the end, where we talked about proteins that have multiple localizations. So we looked up the TF3 transcription factors. And so another visualization that is linked to this one is the profile plots. The profile plots represent the protein profiles, so in the 20 dimensions that are here. And there are 2 proteins. It's very busy here. Let me maybe remove some of the annotations. Okay. So here I keep the 40S ribosome in red that is highlighted. And there are 2 proteins, 2 protein profiles here that are represented in bold. And these are the same proteins that were selected on the PCA plot. So the table and the different visualizations are linked. And one action that is done in one figure is also applied to the other figures. Okay. So this was the visualization of this data, the the interactive visualization of this data locally. And now the kind of third aspect, the third that brings us back to one of the points that were mentioned by Niels, is sharing of the data. So let me open this in a new tab. This Shiny app can also be uploaded to a server, and these could be local servers, or in this case it's an infrastructure that is provided by RStudio, and RStudio is the company behind Shiny and GGBase and so on. And so there is also an online application. It is with the same data set. We will recognize the PCA plot. But now that everybody can access, it has R and Shiny running on this server without having to install R, the packages, and the data locally. So the kind of set or suite of packages that we have for that use case is a package Prologue that is used to apply the machine learning to the data, a package that provides data, so Prologue data. We wanted to add interactivity, so we developed a Prologue GUI package that allows us to visualize this data interactively using Shiny locally, and then the next step is to port or to upload these applications on the server to kind of bypass the requirement to use R locally, if we want. And so what I would like us to do together for the rest of this session is to write a Shiny app together. So it will not be based on proteomics, but I would like us to write this application together using Shiny. So could you all please load the package library, the package Shiny, if not install it with install.packages, and in case there is a problem when installing and or loading, please call us and we'll try to fix it. Once Shiny is loaded, using here, library Shiny, please put your blue sticky notes up. Right, so Shiny uses a programming principle called reactive programming and is composed of two parts. One is the UI, the user interface, and the other part is the server. And these two parts, the kind of front-end user interface and the back-end, the server, interact with each other by using these reactive programming principles. Any change that is triggered at the user interface, any change at the user interface triggers an action at the server part, and itself kind of triggers a reaction from the user interface to update a figure, for example, based on the input. The user interface defines different components that we see as users, such as the page layout, title, and so on. It also defines the user inputs, how we interact with the application, and it also displays the user outputs, like the figures, the tables, and so on. And the server manages the computation on the R side at the back end. So the data set that we are going to use to develop our Shiny app is it's called Faithful and it provides waiting times between eruptions of a volcano. It's a data frame with 2 columns, and that is the data set that we are going to use. And actually, let me show you the application that we're going to write. It's here. So it's available online. Let me reload it here. And so this is what we're going to write together. Here's the application. So in terms of user inputs, we will be able to provide some user text, user-defined text that is displayed here. We will also, as outputs, we will have a histogram, which is the histogram of the times between eruptions. We will be able to change the number of bins to update our histogram, change the coloring of our histogram. And the last part of this application is a table, a data table, that provides the intensity of eruptions and time weighting. This is a table that can be sorted, and we can also search the table. 45, and here are then the columns with the 45s. So this is the application that we are going to write together. So how do we develop Shiny applications? So the Shiny applications, we have two files, and these files need to live in a directory. So first step, could you take all your blue sticky notes down? So the first step is to create a directory. So I will call my directory Shiny App 1. That doesn't matter. And in that directory, you need to create two files. One file, ui.r, and the second file is called server.r. Okay. So let's do that together. I'm going to say, I'm going to create Shiny App. Okay. Create is like, so I'm doing it in R, but you can use your browser. So here, you see, I created this directory, Shiny App. And then in Shiny App, is it file.create? Yes. We need a file ui.r and a file let me show you here in the browser. This is what we need to have. Okay. Server.r, ui.r. So when you have your directory and you have two files, could you put your blue sticky notes up, please? You don't need to create these in R. So this is an R command to create a directory, called Shiny App in my working directory, and this creates a file called ui.r in Shiny App. But feel free to do it with File Explorer or the console, whatever you feel more confident in. For me, it's easier to stay in R. Otherwise, I need to change Windows, and I'm not comfortable with that computer. So we will need to open ui.r and server.r. These are the files that we're going to modify. Is there any question? So I don't see all the blue sticky notes. So if you don't do the exercise, that's fine. Just put your blue sticky note up so I know that I don't need to wait. Okay, great. So let's start by produce this, or start to edit the ui.r file. So we're going to say here, library Shiny, we need to load Shiny at the beginning of our file. So we're going to set up a Shiny user interface. That is the kind of the top level function that we need to call. And then we are going to create a fluid page, which is a kind of one type of page that we want to define to set up the user interface here. So the syntax will be a little bit strange, maybe. Be careful, when you need commas and so on. It's very easy to forget commas here. Okay. So we define the user interface, and we define the page, the HTML page that will contain the whole user interface. We want to have a title panel with a title, My Shiny App, for example. Okay. And here, don't forget the comma. And then I need to specify a specific layout. How will what will be displayed and where will things be displayed in my HTML page? And here I want a sidebar layout with a sidebar panel. And a main panel. So we haven't achieved very much at this stage, other than creating the kind of framework, the HTML page, creating a user interface, creating an HTML page that contains a title and a specific layout with a sidebar and a main panel. And actually, in the when I showed the application, there was a sidebar, but actually the window was too small, and so the sidebar showed at the top. So the part where I wrote the text with the slide bar input to change the number of bins, choose the color and everything, that was the sidebar layout, but it was at the top because of width constraints. So let's go now. Oh, could you put your view sticky notes up, or take them down and put them back up once you have written here the first implementation of our user interface. And by the way, this code is also available in the lecture notes, so feel free to copy and paste, or at least the first step, and then we're going to add things. Good. Server.r, library Shiny. And so the top function here to define a Shiny server is Shiny server. And so the input to this function is function input, output.
Sorry, did you do the other thing in the UI.r?
Yes.
Okay.
Yes. This is UI.r, and the web page is the user interface. And this is the server. And at this stage, what do we have in the server? We define a Shiny server, and we're going to write a function that does all the calculations for us. And the server gets some inputs and returns some outputs. And so what we can already do at this stage, let's make sure that we save user UI and UI.r and server.r, is to run Shiny, the run app function from Shiny, and we pass it the name of the directory. So let's see, I run this, and here's what I get. Let me maximize here. This is my fluid page that I see. At the very top, I have my title panel. What I see here is my sidebar panel, and what I see here is my main panel. There is so far I haven't put anything in these panels, but that is what we have created. There are no inputs yet and no outputs yet. Yes? Yes, yes. So to start this, here we use the run app function from the Shiny package. So could you take all your blue sticky notes down and put them back up or leave them up if when you run run app with the name of your directory, you obtain this page. If you get an error, be mindful of the comma, of these commas here.
Can you go back to the shiny.r?
Which one? UI or server?
Server.
Server. Yep.
You don't seem to name the file.
Yes, here it's called server.r. It's written here at the top, and here UI.r. And they're shown here in the directory.
Yeah, but it doesn't sound like server art calls UI.r.
Oh, no. These two files are in the same directory, and we call run app with the name of the directory. And the run app expects to find UI.r and server.r.
It's a standard naming?
Yes, yes. If you don't like to create two files, you can also create one file and then create a list that contains a server and a UI. I'll show you later, but that is the standard way of doing this. So something that I failed to mention is that, you see, so here's my Shiny app that runs in this kind of R server, and it is displayed in this new RStudio window. Before doing anything else, I need to close this window. Either close this window or press on the stop button here. To kind of, when we start the Shiny app, the session is busy. I cannot use the R console anymore, it's busy, because it's running the Shiny server. Okay, so I cannot do anything new or start a new application. I first need to manually, explicitly kill the Shiny app and then the terminal. Okay. I think the most difficult is done. It just gets started. And now things are going to get more interesting because we're going to add inputs and outputs to our Shiny application. So let's move back to user interface and add an input in our sidebar panel. And the first input would be a text input. So that's a kind of a field where the user can type some arbitrary text. Now we first need to provide here the name. How are we going to name this input? So the function text is the function to create that display that kind of input is text input, and I'm also going to call it text input here. And that's the name of the variable, if you want, that I will need to remember and also use in my server implementation.
So you could say X if you wanted, or
you could, yes. And we can enter your text here, provide some default input. So in the sidebar panel, we have a field where as a user can type things in. And in the main panel, I will want to add a text output. Okay, so I have a text input. The corresponding type of output would be text output. And what do I want to display in my text output? The content of this variable, if you want, text input. An input of type type text, an output of type text. This piece of data is named text input. That's what I define here as part of my input. And I will want to display this text input. I could have multiple text inputs, so I could call this one text input 1. I could have a text input 2, and so on. And so I have to refer which one do I want to display here. And that's where it's input. Yes?
If you have multiple inputs, is it comma separated or?
No, you would have multiple text inputs, different boxes, different fields. If, as a user, I type input 1, comma input 2, then this would be a long string, comma separated, that are all part of text input. So here we manage our inputs and outputs at the user, at the UI level. Now, in the server, we need to do something with these. So the actions at the R level, in the R backend, are written inside this function definition. So I have an input, $text input. Okay. Input here contains all the inputs that are passed from the user interface. And the one that I'm dealing with now is called text input, that I have defined in my user interface. So this contains the character that was typed by the user. So I will, for example, want to paste you have entered and then the actual value of the text input. So this is our code, this is standard out code that takes this character and pastes it after you have entered.
Does like hyphen T and new lines work the same as like other languages?
Hyphen T for tab, yes,
Yeah,
yes.
Tab and, not
Yes.
hyphen, but
Backslash, yes,
backslash.
yes. So here, using this character, I create what I want to display in my output, and I need to render it in a specific way using render text. I can have different types of inputs. We align these properly. And that's some shiny syntax. Here I create some text using my text input, and I need to render it properly. Now, here I use my input variable. I also need to use my output variable. Output, $text output. This is where I want my text, this is how I now update my output. What output specifically? The text output using an input, which one specifically? My text input. Server.r, UI.r. Once you have done this, I see here that I have a run app.button. Maybe I can, let's try. I'm going to click it and see what happens. It works. Hello? Not quite. Not quite because my text is not displayed. it should display here. Text output.
How
Panel.
would I display it?
Pardon?
GIF display.
Here I render it,
Okay.
and I render it in this part of the output.
Don't you have to in the UI.r, if you go up, should it not be text output? Yeah.
Ah, yes, you're right. Yes. So this is how I call my input, this is how I call my output. And here I want to update this specific output. Thank you. So could you put your blue sticky notes up when you have added this first level of interactivity and reactivity to your app? Good. Let's add some additional inputs and outputs. Back in the user interface, let's add a plot output. And I'm going to call this plot. Oh, and I must not forget a comma here. So there are different types of outputs that I can have. We have user text output. Now we're going to have a plot output. So this updates the user interface so that in the main panel, under the text output, we want to have a visualization, a plot. And in server.r, we need to produce that plot. So here we have output $plot dist or distplot. Let me check. Yes, distplot. So that's the name of this item. And I want to render it, create it using the renderPlot function. And in renderPlot here, I will write some code that will produce the figure that I want. We want to use the faithful data and the second column of the faithful data. So my data of interest is in X. And the way I produce the visualization is with the hist function. By the way, you could also have ggplot code here, or base, it doesn't matter. So this is the part of code that renders the text output. This is the part of the code that renders the dist plot. Here it is. So there is currently no interactivity for the plot because we only have one output, and that output is used to update the text output. Okay. So UI interface, we add plot output that here I name this plot. And in server, I render, or I update. In this case, it's updated once. This plot is rendered with the function renderPlot. These are the two lines of R code where I produce my data, my vector of numbers, and here I display it with a histogram. Could you keep your blue sticky notes up if you get the app? If the app works like this, or take it down if it doesn't work yet, or call me if there are any questions. If you have an error, make sure you have a comma here after text output. Okay, can we carry on? Good. Now we want some interactivity to update our plot, the histogram. So we need some new input that we're going to add to the sidebar panel. And the type of input that we want here is a slider input. So how are we going to call to refer to this type of input? In the server part, we are going to call it bins. Let's provide a little label to this input when it's displayed in the user interface, number of bins. And this slider, we want it to start at 1, to finish at 50, oh sorry, 2, yeah, max 50, and to start with a default value of 30. And I need a comma here. And here. In the user interface, a second input, and this time it's an input of type slider. This is the name of this variable, this element that we will use in server.r. The label, and we want the slider input to go from 1 to 30 with a starting value of, from 1 to 50 with a starting value of 30. If I come back to server.r, I'm going to update this piece of code that renders my histogram, but before that I want to, here, the argument in R to modify the number of breaks or number of bins in histogram is breaks equals bin. And where do I get bin from? So I will have to create a variable bin here, and that what comes from input $bin. Input $bin, because that's how we called the slider input variable. So this needs to be adapted max x blank dot out equals and actually it was called bins equals 1. Check. Bins, yes. So this is some R code to set this value properly. I'll give you a minute to update. The rendering function.
What does the breaks, so I get what the bin does, but what does the breaks do?
So let's show here. I'm going to create an X that contains 100 values drawn from normal distribution, histogram X. Breaks equals, let's say, 50.
Okay.
It allows us to modify the number of bars in our histogram. And that is what we want to be able to control interactively. So, unless I have done any typos, I should now be able to run my application. And I have 2 user inputs. Here, and my my slider input that allows to control how my histogram is displayed. Does this work for you? Could you put your blue sticky notes up if it works, or the yellow ones if you have a question? So here we create this variable and we use it here to render, to redisplay the plot based on changes. So I'm going to show you in the lecture slides what needs to be added, but it's the same idea to add the coloring. Here, we want to be able to select the different colors. We have a select input that we call col, a little message that's going to be displayed, and here the choices: steel blue, dark gray, and orange. So this is an input displayed in our side panel, and here's how we use it when displaying the histogram. We say col equals input$col. This is how it's called in the user interface, and col is a parameter to hist. And finally, if we want to have the table displayed at the very bottom, that is another type of output, a data table output that we call data table. And so for the outputs, we have the text, the plot, and the data table output. And in the server, we need to display it, to render it, using render data table. And then the data set that we want to display, and in this case, it's a faithful data frame. And so we update the output data table. And this will produce the fully functional Shiny app that we had at the beginning. So we could also have a single file. Instead of having UI.r and server.r, we could have a single file where we create a UI, bullet page, we create a server with the function input output, and then we create a list that contains the UI and the server, and then we would say run app with the name of this list. And so how to share these Shiny applications? You could share the file or files with people. You can also provide them at the URL. So there is a run URL function to run these files if they're located somewhere else. You can also store them on GitHub or store them as GitHub gist. You can install Shiny server or kind of in-house server that will know how to handle these Shiny applications, or you can use Shiny apps provided by our studio to host these applications on their servers, like the applications that we demonstrated before. There is a free plan with a limited number of applications and with a limited number of bandwidth, or you can pay as much as you want to host more applications and get kind of private accounts or kind of specific logins and so on if you need them. So there is more interactivity, for example, in our plot outputs, and that is part of the code for the applications that I showed for the PCA. We can control hovering, clicking, double clicking, and brushing, as I demonstrated for the PCA application. The Shiny page, there is a Shiny cheat sheet, and actually I forgot to mention there is a ggplot cheat sheet and the dplyr cheat sheet that are useful when you're not yet familiar with all the kind of the syntax, and the links to the sheets are provided in the lecture material. Okay, So that concludes our interactive session, and I'm very happy to put my last tick here. So we managed to go through all the program. I'm pretty happy about that. And so thank you very much for coming and staying to the very end. If you have questions, don't hesitate to get in touch. Send me a little email later on. I'm lg390@cam.ac.uk. If you Google my name, you should be able to find me quite easily. But before we finish, I did not forget to ask you to fill out the survey form before leaving the room, please. Here it is, feedback survey. And do not forget, very important, your sticky notes to provide feedback on this session specifically, but if you have more general feedback, something that you enjoy about the course, and some improvement that is needed. And when you leave the room, please leave your sticky notes here, and I will read them with great interest. So thank you very much, and you also have your certificates here. Okay?